the problems that we have been doing in the class for lesson number 1 in this video. I'll start with the 14th problem in the exercise because we've already done 13 problems. Okay, let me read the 14th problem and then we'll start doing it. The 14th problem is this, 114. The figure below gives the tracks of 3 charged particles in a uniform electric field. A. Give the signs of the charges, and B. Which particle has the highest charge to mass ratio? Which particle has the highest charge to mass ratio? Okay. The trajectories are like this. Okay. First one is goes like this, one body, and the second body goes like this. Let's say this is one, this is a trajectory, and the second goes straight, and then the third bends much more than the first one. Yes, these are the 3 trajectories given, and they say that the electric field between the plates is uniform. So E is uniform between these 2 plates. We already derived this, right? So when you have a plate, a large plate or an infinite plane sheet, then the electric field will be constant here because of this plate, and you also have another plate here, and because of that too, the electric field will be constant. But these 2 now inside will aid. Why? Because if you bring a positive charge here, this positive plate will push it down, and then the negative plate will pull it down. So there would be a net force. They won't cancel because you have plus and minus there. Anyway, so the point here is that a constant electric field E is maintained between these 2 plates. Now there are 3 charges, charge 1, charge 2, 3 particles, let's say. One is bending upwards, the other one is going straight, and the third one is bending down much more steeply than the first one. Now this is a question, right? Let's see. So clearly, what would be the charge of 1? 1 has to be a negatively charged. Why? Because it's bending towards the positive plate, and it's getting attracted towards the positive plate, and clearly this will also be repelling it. So this must be negatively charged. What about 2? 2 is not deflected at all. It goes straight. It is not affected by the electric field at all. So which means that it must be neutral. It is affected neither by the positive plate nor by the negative plate. So this must be a neutral particle. This cannot have any charge. So this must be neutral. And then what about 3? Well, it bends like that. Okay, much more steeply than particle 1. So clearly that has to be positive. Why? This is a negative plate, so it is bending towards a negative plate. So this must be positive. And the other way of looking at it is that you have positive plates there, so this would push it this way, and this is going to be repelled by the first one and attracted by the second one. So this is how it's going to be. So this must be a positively charged particle. This answers the first part of the question. And then the second part, which particle has highest charge to mass ratio? So what is this charge to mass ratio? This is A, and let's say this B is charge to mass ratio. So charge to mass ratio, that's Q by M. So how do I calculate it? Let's see how this can be applied here. Okay. suppose that the charge here is Q1, okay, and then the mass is M1, and the charge here, okay, here Q is going to be 0, so mass is going to be M2, and the third one would be, so Q3 and then M3. We need to find this ratio, the charge to mass ratio. So how do we find that? It's easy again. So you know this field E is constant, and this charge is going to experience a force EQ1, and that must also be equal to M1 into A1, mass times acceleration. Let me write that equation here. So the force experienced by this is going to be E to Q1, and this must be equal to M1 to A1. So what do we need here? We need the charge to mass ratio. So Q1 by M1 will give you A1 by E. So E is constant. So you can say from this that the charge to mass ratio is proportional to the acceleration that you get. Okay. So this gives you this expression. So Q by M must be proportional to acceleration. Okay. So notice that these particles are moving in this direction, the horizontal direction, but then they are getting deflected in the vertical direction, either up or down. So the horizontal velocity will not be changed by the force. Only the vertical velocity will be changed. Which means that if the acceleration is more, then they will fall or move up to a greater distance. It's like projectile motion, right? So you throw something straight, then the horizontal velocity is not changed at all, but then the vertical velocity will be changed because if you start from 0 speed vertically, so it will start falling as it's moving in this direction, right? And the amount of fall depends on the acceleration. Okay. Likewise, if it gets attracted upwards, as it happens here, again this force E will not affect this one, will not affect the horizontal speed. It will only change the vertical speed. So you can see that this acceleration is smaller because the deflection is smaller there, but the deflection is much greater here. So this particle has a greater acceleration than that one. So what can I conclude from this expression? From this expression I can say that Q1 by Q3 by M3 is equal to A3 by E. But then Q3 is falling faster than Q1. So which means that this acceleration is more than this acceleration. Which means that the charge to mass ratio of 3 is greater than 1. So which particle has highest charge to mass ratio? Clearly particle 3 has the highest charge to mass ratio. This is how you do this problem. The two things that you need to remember. One is the field is constant and particles are getting deflected. So if something is getting deflected towards the positive plate, this must be a negative charge. If something is getting deflected towards the negative plate, then this must be positive. So Q3 is positive and Q1 is negative, and Q2 must be 0. Okay, I call it Q2. This must be 0. Okay. All of them can have different masses. All of them can have different speeds here. The horizontal speed doesn't matter at all. Then when you try to find the charge to mass ratio, you are going to equate the force with the mass times acceleration. I'm going to use this expression. So this is a force. From that I can find the charge to mass ratio, which must be A1 by E. That gives you the expression that Q by M must be proportional to A, because E is a constant anyway. So the charge to mass ratio must be proportional to the acceleration you experience. But where is this acceleration? This acceleration is only in the vertical direction. Okay? In this case it's up. In this case it is down. So the greater the acceleration, the greater the charge to mass ratio. So particle 3 has the greatest charge to mass ratio. Hope this is clear to you. 1.5. Consider a uniform electric field E, which is equal to 3 into 10 to the power 3 I Newton per coulomb. Okay, this electric field is along the x-axis and it is also uniform. Now the questions are: A. What is the flux of this field through a square of 10 cm aside, whose plane is parallel to the YZ plane? And that's the first question. And the second question is: what is the flux through the same square if the normal makes an angle 60 degrees with the x-axis? Here the normal is the normal of the square. Okay, so these are the two questions. So let's see like how to do them. First one, A. First of all, let's see like where the field is. It is E, which is equal to 3 into 10 power 3 I Newton coulomb. So if I take this to be the x-axis, okay, this is x, then I is in this direction, right? Okay. Now this must be my y. So I have j vector in this direction. So this must be my z. Then I must have k vector in this direction. There is positive I, positive j, and then positive k. So E is in this direction, and it is uniform. At every point you take here, every point you take, and E is like this, like this, like this. Okay. A is in this direction. So the magnitude of that is 3 into 10 power 3 Newton per coulomb. And your plane is okay. You are going to take a square of 10 centimeter like this, and that is parallel to the YZ plane. So which is this, right? So you have x here, y there, and then z there. So YZ is this plane. So on the side, YZ, it's a plane. So that is going, you are going to keep it like this, right? So this x, and then this is the square. This is parallel to the YZ plane. Okay. Now what is the flux through it? That's easy. So what is phi? Phi electric flux is equal to E dot area, right? Area. Okay. So that gives you E A cos theta. This is a dot product, so it's a scalar quantity. So if I take a plane like this, then the vector, the normal to the plane, that is going to be treated as the vector of that square, and that is also in the same direction as E, because the plane is parallel to the the square is parallel to the YZ plane. So the normal that you draw would be along the x-axis. So the plane, the normal to the square is also parallel to E. So cos theta, here theta will be 0. So theta is equal to 0. So phi E simply becomes EA cos 0, which is 1. So that is simply E into A. So what is E? E is equal to 3 into 10 power 3 Newton per coulomb. And then A is 10 centimeters, so 0.1 meter into 0.1, that's the area, right? So that's going to be equal to 10 centimeters, so 1 by 10 meters into 1 by 10 meters. So you have here a 2, then this will become 1. So I'm going to have this area, meters square. Okay. So that will give you 30 Newton meter square per coulomb. That's the flux through the square. That's your A part. And what's the B part? The B part is that the plane, the square, instead of being parallel to the YZ plane, now it's going to be tilted and it's going to make an angle 60 degrees to be even. Okay, so the square is now going to make an angle 60. Now it's like this, right? Right now, it's like this. When I tilt it 60 degrees, so this angle between E and the normal is going to be 60 degrees. And what would phi be then? So phi E is equal to the same E dot A vector E A cos theta, but now theta is equal to 60 degrees. Let's see the angle between E vector and then the normal of the square. So phi E is going to be equal to E A cos 60. Cos 60 is 1 by 2, so E A to 1 by 2. So E A already calculated to be 30, 30 by 2 is equal to 15 Newton meter square per coulomb. So that's the flux. So the answer here is phi E is equal to 15 Newton meter square. Okay. So when the normal is parallel to E, the flux is 30 Newton meter square per coulomb, and when the normal makes an angle of 60 degrees with E, then the flux through that area would be just 15 Newton meter square per coulomb. So we have discussed that in the class. So lines are going this way. If you keep it like this, all the lines will go through this. But then as you tilt, then only a few lines will go through this area. And then when it is perpendicular, no line goes through it. So any angle more than 0 should reduce the flux. So this is how we do this problem. It's an extension of question number 15, and then this is what it says. What is the net flux of the uniform electric field of exercise 1.15 through a cube of side 20 cm oriented so that its faces are parallel to the coordinate planes? So which means that you have the same thing. Okay, see, same 15. E is in this direction. E is in this direction. Okay, and I direction. And I'm going to have a cube like this, right? So it's like that. So, and then the sides are parallel to the coordinate axis. So which means that that E is going to come out like this. And then E will enter like this because E will have the same direction, right? So it will like this. So you can see that the amount of flux that is entering one side is equal to the amount of flux which is leaving this cube. So the net flux through this cube will be 0. Of course, there is no E in this direction or in this direction, right? And E is only in the I direction along the x-axis. So if I assume a cube here, then this is the x-axis. The amount of flux which is entering through this side will be equal to the amount of flux which is leaving this side. So the net flux through the cube will be 0. Problem 117. A careful measurement of the electric field at the surface of a black box indicates that the net outward flux through the surface of the box is 8 into 10 to the power 3 Newton meter squared per coulomb. Then what is the net charge inside the box? The second question is, if the net outward flux through the surface of the box were 0, could you conclude that there were no charges inside the box? Why or why not? Okay. It's a very simple problem. You may know how to do this. Let me do it. Anyway, so on point 17, the flux through the surface of a black box. Let's say it's a box like this. You don't know what is inside, so that's why you call it as a black box. So flux may be coming like this, like that, never know. Okay, so you make a careful measurement of all the flux that is coming out of it. And then you find that flux to be equal to 8 into 10 to the power 3 Newton meter square per coulomb. This is the flux which is coming out. So then what is the net charge inside? You know, that's the Gauss law. So you know that the electric flux which is coming out must be equal to Q by epsilon naught. So Q must be equal to phi E into epsilon naught, and that must be equal to 8 into 10 to the power 3 into epsilon naught is 8.854 into 10 to the power minus 12. Right? Okay. So effectively this is something, it's like 9. So 9 8s are 72, then 10 power minus 9. So 72 into 10 power minus 9 coulomb. So that is what you get. Okay. It's like 72 nano coulomb charge. Okay. Well, that is inside the black box. So that's the first part of the problem. Then the second part is this. If the net outward flux through the surface of the box was 0, could you conclude that there were no charges inside the box? Suppose there is no net outward flux. Can you conclude that there is no charge inside? No, you cannot. All that you can conclude is that there is no net charge inside. Maybe there is an equal amount of positive and negative charges, thus Q and minus Q kept here. Then the net charge is 0. The net charge enclosed is 0, so the flux will be 0. But you cannot conclude that there is no charge inside. There could be charge. But then there is an equal amount of positive and negative charges inside the box. And that is what you can conclude. There may not be charge at all. Okay, there may be no charge in it, but you cannot say categorically. You cannot say with certainty that there is no charge inside. There could be positive and negative charges, which cancel each other out. So all that you can say is that there is no net charge enclosed in the box. You cannot say there is no charge. There is no net charge. There is a difference between the two statements. No charge meaning there is no charge at all. No net charge meaning there is equal positive and negative charges inside. And that is the only conclusion you can come to. It may be 0, but you cannot say that. I mean, there may be no charge at all, but you cannot say that. Whether there is no charge or there is no net charge, the result will be the same. There will be no net flux. So the safer way to say that is, there is no net charge inside. Question 1.18. A point charge or 10 microcoulomb is at a distance 5 centimeter directly above the center of a square of side 10 centimeter as shown in the figure. What is the magnitude of the electric flux through this square? That's easy. This 180. They're saying that there is a square. Okay? And then directly above this, there is a charge Q. Okay? And this is actually 5 centimeters. Okay? Now they want you to find the flux through this area. So from here, and it could be flux through this, right? So that could be, and send flux through this, So, like that, right? That can be flux through this. So from the charge, you have a charge here, then there's a space here, then flux can go through this surface. So that is what they are asking. So they want you to find, given this information, Q is 10 microcoulomb, right? So Q is 10 microcoulomb, and the distance is 5 centimeters. Then they want you to find the charge, the flux through this one surface. How can you do it? Well, the side is 10 centimeters actually. So this is 10 centimeters, right? So this is 10 centimeters. This is 10 centimeters. And this is 5 centimeters from here. So if I take 10 centimeters, you see, there is an imaginary cube I can fill. Okay? Maybe something like this. I don't know what this is. That's an imaginary cube I can do. Okay? So the charge is at the very center, and it is sending the flux in every direction. Okay? Now they want you to find the flux through this one surface. So this is 10 centimeters, right? So this is 5, then plus 5, and by 10 centimeters one side, and 10, 10. It's like the charge is at the very center of a 10 centimeter cube. Okay, a cube with 10 centimeters as its sides. That's what it means. So what do you know? What's the flux outside? The flux which is coming out of it. So well, if you take this closed surface, the charge enclosed is Q. So the flux which is coming out must be equal to Q by epsilon naught. There's a total flux which is coming out of this closed surface. Whether it can be a sphere or it can be a cube, anything, any shape you take, even if there is an irregular shape, then the amount of flux which is coming out of the surface is equal to charge by epsilon naught, the charge enclosed in the surface, and divided by epsilon naught. That we know from Gauss's law. So I can find the amount of flux coming through all the 6 sides of this cube. Total flux, all the 6 sides will be equal to Q by epsilon naught. But then there is only one side. So the amount of flux which is coming through one side must be the same as the amount of flux which is coming through other sides, because this charge is at the very center of the cube. What is it? So only 5 centimeters here, it's 10 centimeter width. So this is very center, then 10 centimeter, 10 centimeter, 10 centimeter, 10 centimeter. So you see, the charge is at the very center of the cube. So the amount of flux which is coming out of one side must be the same as the amount of flux which is coming out of another side. So the total flux divided by 6 will give you the amount of flux which will come out of one side. So the way to do this problem is to find the flux which is coming out of one side is equal to 5 by 6. So what is 5? Is Q by epsilon naught. What is Q? Q is 10 microcoulomb, right? 10 into 10 power minus 6 divided by 8.854 into 10 power minus 12. So minus 6, and this will be minus 6 here. So that will go. So 10 by 9 roughly into, it's equal to 10 by 9 into 10 power 12. Okay. So this is the amount of flux which will come out of that. Newton meter squared per coulomb. So that's the flux, right? Okay. So Newton meter squared per coulomb. That's the amount of flux which is coming out. The entire flux. So pi by 6 will be 10 divided by 6 into 9, 10 power 12 Newton meter squared per coulomb. So this is 54, that is 10. So take one more, 100 by 54, roughly 2, okay, so maybe 1.8 or 1.9. I'll say 1.9 or something, okay, into 10 power 11 Newton meter square. Good. So this is the amount of flux which will come out of one surface. We check the answer. Yeah, it's given us 1.88. Oh, okay. So, look, this is 6. 10 power minus 6 here. So this should be 6. I'm sorry, and this should also be 6. And this must be 5. Okay, so it's 10 power minus 6 to 10 power minus 12 will give 10 power minus 6, and when it goes up, then that is 10 power 6. Then you get something like this. So 1.9 into 10 power 5 Newton speed. Okay. So that is problem number 18. Then problem 19. A point charge of 2 microcoulomb is at the center of a cubic Gaussian surface 9 cm on edge. What's the net electric flux through the surface? A point charge of 2 microcoulomb is at the center of a cubic Gaussian surface. So that's a cubic surface. We call it as a Gaussian surface. And then you have a point charge of 2 microcoulomb is at the center. And the size of that is 9 cm on the edge. Okay. Then what is the net electric flux through the surface? For that you don't require anything else at all. So if there's a cubic 1.19, right? So you have a cube. There is a charge of 2 microcoulomb at the very center of the cube. So the amount of electric flux which is coming out, phi e is equal to Q by epsilon naught. So this is 2 microcoulomb, 2 into 10 power minus 6 coulomb. So epsilon naught is going to be 8.854 10 power minus 12. So it's going to be 2 by 9, right? So 2 by 9 into 10 power 6. So 2 by 9 roughly into 10 power 6 Newton meter square per coulomb. So you can do 20 by 9, that would be 2.2 into 10 power 5 Newton meter square per coulomb. So that is, it's a very simple thing. Because like you're keeping the charge of 2 microcoulomb at the very center of a cube. So it's a Gaussian surface, an imaginary surface. And the amount of flux that is coming out of the surface through all sides of the surface will be equal to Q by epsilon naught. And this way you can find the total flux which is coming out of it. In this case, the 9 centimeter information per side is not even needed. It's an extra piece of information. You don't even need it. I'll do it like this. Hope this is clear to you. Now let's do problem 120. A point charge causes an electric flux of minus 1 into 10 power 3 Newton meter square per coulomb to pass through a spherical Gaussian surface of 10 centimeter radius centered on the charge. If the radius of the Gaussian surface were doubled, how much flux would pass through the surface? Well, what's 120? A point charge causes an electric flux of minus 1 into 10 power 3 Newton meter square per coulomb to pass through a spherical Gaussian surface of 10 centimeter radius. Okay, so the flux is equal to minus 1 to 10 power minus 3 Newton meter square per coulomb. So this is the flux. What will happen if I double the radius of the surface? Will the flux increase? No. We have done that already. We have discussed this in detail before. Increasing the size of the sphere will not change the amount of flux lines which come out of it. Whether it's a small sphere or a big sphere, then the flux lines will be the same. There won't be any change in it. So to answer the first question, if the radius of the Gaussian surface were doubled, how much flux would pass through the surface? The answer is the same amount. There will be no change in the amount of flux that is passing through the surface. And then, what is the value of the point charge? And that's easy. Well, the value of the point charge is very easy, right? So the phi is also equal to Q by epsilon naught. So it's a point charge. So Q must be equal to phi into epsilon naught. So minus 1 into 10 power minus 3 into 8.854 into 10 power minus 12 totally coulomb. So this must be minus 8.854 10 to the power minus 15 coulomb. So that must be the amount of charge. So it's a negative charge which is so small, 10 power minus 15 coulomb. So that's the answer to that question. Next one is 1.21. A conducting sphere of radius 10 cm has an unknown charge. If the electric field 20 cm from the center of the sphere is 1.5 into 10 to the power 3 Newton per coulomb and points radially inward, what is the net charge on the sphere? So we have a conducting sphere there is a center. So there is charge on the sphere. You don't know what charge it is. So there is some charge Q on the surface of the sphere. Okay, so this is the center of the sphere. The charge is on the surface of the sphere. What does it say? It says that the radius is 10 centimeters. The radius is 10 centimeters. It has an unknown charge Q. If the electric field 20 centimeters from the center of the sphere. So from the center, if I take 20 centimeters, this part. So this is also 10 centimeters, right? So totally 20 centimeters. So there is this field E. It is 1.5 into 10 to the power 3 Newton per coulomb and points radially inward. So it's like this. E is in this direction. E is equal to 1.5 into 10 to the power minus then to the power 3 Newton per coulomb. So this is the field strength and then it is pointing radially inwards. So what does it mean? Well, you have, if I bring a positive test charge, then that is going to be pulled inside. Which means this charge Q must be negative, right? So I will have negative charges on this, and that is why this is getting pulled radially inward. The unit positive discharge will be pulled this way, and that is the direction of E. Okay. So what is asked now? What is the net charge on this sphere? That's easy. Why? See, this is a point which is outside the sphere. So what did we say for points outside the sphere? For the points outside the sphere of charges will act as if all the charge were concentrated at the center of the sphere. Okay? So it is like having a point charge here. Okay? And at this point, this is the field you get. Suppose if there were a point charge Q there at the very center, then what is E here? E will be equal to K Q by R square. If there were a point charge, there is no point charge as I keep saying. If there were a point charge here, then E would be like this. But you have a sphere of charges, but then you are talking about a point which is outside the sphere. So for the points outside the sphere, the sphere will act as if the charge were concentrated at the very center. Okay? And I can replace the whole sphere with a point charge, Q. So that is what I get. Well, this radiating inward, so I get minus M. Okay? Or I will say minus E is equal to KQ by R squared. So then what is Q? So Q is equal to minus E R squared by K. So 1.5 minus negative charge, 18. To 10 power 3, what is R squared? R is, now it is 20 centimeters, right? So 2 by 10, I will say, 2 by 10 into 2 by 10 meters, and divided by K is 9 into 10 power 9. Okay, so this and this will go, we will have just 1. So this will go, we will have 8. Okay, so this is 4. 4 into 1.5 will be 6. 6 by 9. So minus 6 by 9. Take it up to 10 to the power minus 8. So it's going to be 2 by 3, right? So Coulomb. So it's going to be minus 2 by 3 into 10 power minus 8 Coulomb. So there is a negative charge of minus 2 by 3 10 power minus 8 Coulomb. Or minus, and so I can also change it, right? I can multiply this by 10, divide that by 10, so then give me minus 20 by 3 into 10 power minus 9 Coulomb. So that is also equal to minus 6.67 into 10 to the power minus 9 Coulomb, or minus 6.67 nano Coulomb. Okay, that's the amount of charge you have on the sphere. That amount of charge would behave as if it were concentrated at the center. Is it concentrated at the center? No. It is distributed over the surface of the sphere. But it would behave as if it were concentrated at the center. It would behave as if it were a point charge acting from here. Because the point where you are finding the field is outside the sphere. Okay, so this is the answer for 1.21. Question 1.22. So, conducting sphere of 2.4 meter diameter has a surface charge density of 80 microcoulomb per meter squared. A. Find a charge on the sphere. B. What is the total electric flux leaving the surface of the sphere? That's easy. Okay. So what is given here? So 1.22. Diameter of the sphere, that is a sphere. Okay. So the diameter is given as 2.4 meter, which means radius must be 1.2 meters. Okay. So that is given. So the radius must be 1.2 meters. And what else is given? The surface charge density is given to be 80 microcoulomb, okay, per meter square. So what's the total charge? The total charge is simply the surface charge density multiplied by the surface area. That's the total charge, right? So the total charge Q is going to be equal to charge density multiplied by area. So that is going to be equal to 80 into 10 power minus 6 Coulomb multiplied by what is area? Surface area of a sphere, 4 pi r squared. So 4 times pi 1.4 into 1.2 the whole square. Okay. So what I'm going to get here? So this is roughly 1.44. Just do that. 80 into 10 power minus 6 into 4 into 3.14 into 1.44. I mean, I can take this to be 1.5 into 3, 4.5. 4.5 into 4 will be 18. 18, roughly 18 into 8. So that would be 28, 8 would be no, okay, 80 plus 64, that is 144, I suppose, right? So 144 is something. So it's actually 1.45 is what you're getting. So 1.45 into 10 power minus 3 is what you get. Plus 80 into 20. So into 10 power minus 6 will give you 1.45, 10 power minus 3. So it's just arithmetic operation, so which you can do very easily. So this is what it is. So you get Q like this. And what is the second part? What is the total electric flux leaving the surface of the sphere? Simple, right? Total electric flux leaving the surface will be equal to Q by epsilon naught. Anyway, it's 1.45 into 10 power minus 3 coulomb is the total charge on the sphere. So divided by is 8.854 into 10 power minus 12. Okay, so Newton meter square per coulomb. So this gives you, this is around 9, so 9 1.45 and 1.6, so 10 power 9, 10 power 8 or something. Okay, 1.6 into 10 power 8. 1.6 into 10 power 8 Newton meter square. So very simple problem. So they have given you the surface charge density and then the radius. So what is total charge on the sphere? The surface charge density multiplied by the area. So you get that. And what's the flux? That is simply Q by epsilon naught. Q you know. Divided by epsilon naught will give you this answer. It's very straightforward problem. Nothing complicated about it. Okay. So 1.23. An infinite line charge produces a field of 9 into 10 power 4 Newton per coulomb at a distance of 2 centimeter. Then calculate the linear charge density. So 1.23. So there is an infinite line. Okay. So it has a charge density lambda, linear charge density lambda, and they say that at a point which is 2 centimeter from here, from the line, then we get a field of 9 into 10 power 4 Newton per coulomb. So there is a field E, you know, it's always going to be up, right? So E is equal to 9 into 10 to the power 4 Newton per coulomb. Newton per coulomb. So this is given to be R is equal to 2 centimeters. Okay. Then the question is calculate the linear charge density. What is lambda? We know this, right? What is E? E for an infinitely long line is equal to lambda by 2 pi epsilon naught R. So from that we must be able to find lambda. So it's lambda now. So lambda is equal to E into 2 pi epsilon naught R. What is E? 9 into 10 to the power 4 into 2 into 3.14 for pi epsilon naught 8.854 into 10 to the power minus 12 for epsilon naught, and then this would be R 2 into 10 power minus 2 meters, 2 centimeters per minus 2. So it's easy. Okay, it is roughly 9, 8.854 is 9. Okay, so 9 into 9, 81, and then 4 into 3, 12, 12 into 81, somewhere around 96, right? 96 something. So this is going to give you roughly 10 power minus 7 coulomb per meter. Okay? So 10 power minus 7 coulomb per meter. That makes sense actually. If you just take this 10 power minus 14, 4, so 10 power minus 10 is what you will have, and then as we just calculated, you will have 96 you know, so you effectively will end up with 10 power minus 7. Okay, that's it. 81 into, it's 81 into 81 into 12. So 8, 10 to 12, so 960. Okay, 960 is what you will have. 960 into 10 power minus 10. So 960 can be treated to be somewhere around 1000 into 10 power minus 10. So we will get 10 power minus 7 coulomb per meter. So easy to do. It's not difficult at all. Okay, so that is 1.23. So what about 1.24? 1.24 is this. Two large thin metal plates are parallel and close to each other. On their inner faces, the plates have surface charge densities of opposite signs and of magnitude 17 into 10 power minus 12 coulomb per meter squared. Then what is E in the outer region of the first plate, B in the outer region of the second plate, and C between the plates? Okay, so two large thin metal plates, meaning it's like you can treat them to be an infinite plane sheet. Okay, so two thin large metal plates, okay, with opposite charges. So there is a plate here and there is also a plate here. Okay, large, it goes on. Okay? It's a large plate. I'll stop it here. So this one has positive charge and then the other one has negative charge on the other side. So now the question is, and then they have given the surface charge densities also. So sigma is the same for both. Sigma for this is equal to 17 into 10 power minus 22. 17 into 10 power minus 22 coulomb per meter square. And this must be sigma is equal to minus 17 into 10 power minus 22 coulomb per meter, because you have negative charge here. So the surface charge densities are the same. Okay. So what are they expecting you to find out? They want the field E in the outer region of the first plate and in the outer region of the second plate. So this is region 1, outside this first plate. This is 1 and this is 2, outer region of the second plate, 2, and then inside this is region 3. They want you to find E in this place. Okay, fine. Let me take a point here. At this point, I am going to bring a unit positive test charge, right? So let's take, I am bringing a unit positive state test charge. So what would this E be? This E would be in this direction, oppose that. So this is E positive. At the same point, what will this do? This will pull it this way. E minus. You may think that they are at a distance. So E of this could be greater than E of this charge, the negative charge. But no, what do we know? If you have an infinitely long plane sheet, it's a huge plane sheet, what do we know? You say that E is equal to sigma by 2 epsilon. You said that the field value will not change based on the distance. See, for linear charge, for line charge, linear charge density, then you will have an R here. But for surface charge density, you won't have an R there. So it will be the same at every point from surface. So E due to this plate and E due to this plate will be the same here because the surface charge densities are the same. So in region 1, E, okay, I'll say E is this and E minus is going to be the same, but then minus will be the opposite direction, right? Minus sigma by 2 epsilon naught at this place. So what is going to happen here? So in region 1, E plus E minus vector. Simply, when I add these two, it will be 0. Act in opposite direction. Okay? Then let's come here to region 2. Region 2, what happens? Again the same. Take this point. It's a unit positive test charge, right? So this negative plate will attract it with E, this one. But then the positive plate will push it with E plus. So the net force on this will also be 0 because E minus and E plus will have the same value here also. So E will be 0 here too. Here also E plus vector plus E minus vector is equal to 0. Okay? Then what about 3? Region 3. Well, it's this region. I take unit positive test charge. Then what will happen here? This is going to push it in this direction. That is E plus. And what will this do? That will also pull it in the same direction. So a point here, if we keep a unit positive test charge here, it's going to be experiencing a net force downwards. Now both of them are aiding each other. Okay? So this one, in this case, E is equal to E plus plus E minus. Okay? So in both cases the vector is again vector, but then E vector, E minus vector is in the same direction as E plus vector. So I won't have sigma by 2 epsilon naught plus sigma by 2 epsilon naught. When I add them, then my E is going to be equal to then 2 sigma by 2 epsilon naught, so I will get sigma by epsilon naught. That's the field inside. So when I keep two plates like this, the field here is going to be 0. The field here is going to be 0. There is no field outside those two plates. But then there is a field inside those two plates. And this is the magnitude of the field value. Okay, so with that, the problems in lesson 1 are come to an end. I'm not going to do the additional exercises. I've just done the first exercise. So additional exercise will not do. Okay, those problems I will not cover now. But then we have done all the problems in the regular exercise. So we covered 24 problems so far. Okay, hope these problems, solving these problems, gives you a better understanding of the lesson. Okay? If you have any questions, get back to me.